All right, let's take a look at this warm up here. Shuffle a standard deck of playing cards and deal one card. Define event J as getting a jack and event R as getting a red card. Fill in the two-way table for this deck. All right, so you have to know a little bit about a playing deck, but there are 52 cards, 26 red, 26 black. There are 4 jacks, diamond, heart, which are the 2 red ones, spade and club, which are the 2 black ones. So when we're filling this in, there's 2 red jacks, there's 2 black jacks, there's 4 jacks in total. All right. Now again, there are 26 red cards. If 2 of them are a jack, that means that 24 are not a jack. Same with black. So there are 48 cards that are not jacks. There are 52 cards in total. And again, 26 red and 26 black. So let's go through and run through these various probabilities. So probability of getting a jack. All right, this is not a conditional probability, so we're going to be using these totals here. It would just be 4 out of 52. Probability of getting a red, 26 out of 52. Now, probability of getting a jack given that the card is red. Now we're looking at this row right here, and we would get 2 out of 26. And this is saying probability of getting a red given that it's a jack. Now we're looking at this column. All right, we're telling you that it's a jack, so the probability of getting a red would be 2 out of 4. Now, the final question there says, are the events J and R independent? Now, remember, to prove independence, we have 2 options. We either have to prove that the probability of J is equal to the probability of J given R, or we can show that the probability of R is equal to the probability, of R given J. All right, so we're checking. That's why I put the little question mark over. We're checking to see whether or not those are equal. So the probability of getting a jack is 4 out of 52, which is, we'll say, 7.7%. All right, the probability of getting a jack given that it's red is 2 out of 26, which is that same exact value. All right, it's just the fraction reduced a little bit. So those are equal. Now, if we went in the other direction, it's probably easier. 26 out of 52, pretty easily 0.50 or 50%. Probability of red given jack is 2 out of 4, 0.5. So in this case, yes, they are independent. Independent. All right. The probabilities stayed the same. All right, so here's an example where the events are independent. Now this next one. Suppose you roll 2 fair 6-sided die, 1 red and 1 green. Are the events the sum is 8 and green die shows a 4 independent? Justify your answer. Now again, that leaves us with 2 choices. We're finding the probability of getting an 8, and then we're checking, is that the same as the probability of getting an 8 given you have a green 4? Or, all right, your other option is to say, okay, what's the probability of getting a green 4? And then is that the same as the probability? Why do I always start with the parenthesis when I do my second one? The probability of getting a green 4 given that the sum is 8. All right, so what are these various probabilities? So probability that the sum is 8. All right, now we looked at rolling 2 die before, and you may or may not remember this, but there's like one way to get a 2. There are 2 ways to get a 3. There are 3 ways to get a 4, 4 ways to get a 5, 5 ways to get a 6, 6 ways to get a 7. All right, a 7 is the most common. And then it starts coming back down. So there are 5 ways to get an 8 out of 36 ways in total. Okay. All right, 5 ways to get a sum of 8, and there are 36 different combinations. Now, if we look at this situation, it's telling you that the green die is a 4. All right, so if the green die has to be a 4, the red could still be 1, 2, 3, 4, 5, or 6, but only one of those actually gets us a sum of 8. All right, so once I tell you that the green die is a 4, we effectively have a 1 in 6 chance of ending up with a sum of 8. So we're asking ourselves, is 5 out of 36 the same as 1 out of 6? And in this case, they are not. All right, so 5 out of 36 does not equal 1 out of 6, which shows us that these two events are not independent. Now, in theory, we should get the same answer over here. I mean, not the same numbers, but we should come to the same conclusion. So the probability of a green 4 is just 1 out of 6. All right, there are 6 sides on a die. The probability that the green die comes up 4 is 1 out of 6. All right, now this is saying, all right, you know, if I tell you that the sum is 8, what's the probability that the green die was a 4? All right, so what we want to do here is think about all of the different ways that we can get a sum of 8. And we already said there are 5. So if we think about this and we do the red and the green, we could have a red 2 and a green 6. We could have a red 3 and a green 5. We could have a red 4 and a green 4. We could have a red 5 and a green 3. We could have a red 6 and a green 2. All right, so there are 5 options in total. So if I tell you that the sum is 8, you now know that you're looking at one of these 5 choices. Right? Now, there's only one of those 5 that also has a green 4. So the chances would be 1 out of 5. And we can pretty clearly see that 1/6 does not equal 1/5. So again, you don't have to show me both of these. All right, but you have to show me one of them to prove that the two events are not independent. So again, I'm running out of room here because I did both of them. They are not independent because the probabilities are not equal. All right, and again, doesn't matter which one you do, which way you show it to me, but you have to show one of these two to kind of prove the situation here. All right. Now, the next one doesn't have any calculations. It's just asking you to think about it. So it says select an adult at random and then define the events. T, the person is over 6 feet tall, and B, the person is a professional basketball player. Rank the following probabilities from smallest to largest. So this is just the probability of being tall. This is the probability of playing basketball. This is the probability of being tall given you play basketball. And this is the probability of playing basketball given that you're tall. All right, so it says rank the following probabilities from smallest to largest. So which one is the lowest probability? Which one is the highest probability? So I would say that this one right here is the highest probability. The probability of being tall given that you play basketball. If you play basketball, if you play professional basketball, there's a very high probability that you're tall. So I would say that this has the highest probability. All right? I would say the lowest probability is just playing professional basketball. All right. It's pretty rare to play professional basketball. All right. Not that many people on each team, not that many teams. So not that many professional basketball players. Now that leaves us kind of with these two right here and where they fall. So we're comparing the probability of being tall to the probability of playing basketball given that you're tall. Now, I would still argue that playing professional basketball is extremely rare, even if you're tall. All right, there are plenty of tall people who don't play basketball. So I would say that this right here is probably the second lowest. And I would say that this one right here is probably the second highest. But again, it's just kind of thinking about them, thinking about what they actually mean, and making sure you understand how to read these symbols and interpret what each one is saying. All right, take a look at the back. These are some tree diagram questions. Only 5% of male high school basketball, baseball, and football players go on to play at the college level. Of these, 1.7% enter the pros, and about 40% of those who enter the pros have a career of 3 years or longer. So what is the probability that a high school athlete who plays basketball, baseball, or football competes in college and then goes on to have a pro career of more than 3 years? So we don't technically probably need a tree diagram for this one, but I'm going to make one anyways because I like making tree diagrams. So we've got the first one is college versus no college. All right. And they've got a 5% chance of going on to college, which means they have a 95% chance of not playing after high school. Right? And then this one just ends right here. Right? If they play in college, they have a 1.7% chance of making the pros. All right, so 0.017, which means I'm just going to put done here, which means they're done. They have a 98.3% chance of being done after college. And then if they make the pros, they have a 40% chance of going 3 years plus, which is 40%, which means they have a 60% chance of being out before 3 years is up. All right, so that's what the tree diagram would look like. Now, this one just wants to know what are the odds of competing in college, going to the pros, and then having a career of more than 3 years. So we're just looking at 0.05 times 0.017 times 0.40. All right, but that's what the tree diagram would look like for this situation. And if we multiply those out, 0.05 times 0.017 times 0.4, all right, we get a pretty small number there. Now, notice this is e to the negative fourth. So that basically means you're moving that decimal place 4 spots to the left. All right, so 0.00034. Or you could write that as, I could move the decimal 2 points back to the right and say 0.034%. So either one of those is fine, either this or this. But long story short, it's long odds, which I think everybody sort of intuitively knows anyways. All right, number 5, a player serving in tennis has 2 chances to get a serve in play. If the first serve goes out of bounds, the player serves again. If the second serve is also out, the player loses the point. Here are the probabilities based on 4 years of the Wimbledon Championship. Make a tree diagram for the results of the 2 serves and the outcome of the point. All right, it warns you that the 2 halves of the tree will have different numbers of branches. That's fine. All right, so your first serve can either be in or it can be out. Now, if it's in, you don't have to worry about a second serve. You either win the point or you lose the point. Now, if your first serve is out, then you get to make a second serve, all right, versus this, you're just playing. So this is where you play. That second serve can again either be in or out. If it's out, you've lost the point. If it's in, you have to play, at which point you either win or lose the point. All right, so this is kind of running through all of the different possibilities. Your first serve is either in or out. If it's in, you either win or lose. If your first serve is out, your second serve is either in or out. And if it's in, you either win or lose. Now, let's actually attach the numbers to these. So it says the probability that the first serve is in is 0.59, which means that the probability the first serve is out is 0.41. All right. It says the probability of winning given the first serve is in, so that would be this branch up here, is 0.73, which means the probability that you lose it must be 0.27. All right, notice how each node, they add up to 100. 59 and 41 adds up to 100. We've got a new node here, 73 and 27 adds up to 100. All right. Down here, here's our second serve. It tells us the probability that the second serve is in, given that the first serve is out, is 86%, right? Because you usually do a safer serve if your first one went out. So 86% chance that it went in, which means there's a 14% chance that it went out. And then last but not least, the probability of winning the point given that the first serve is out and the second serve is in is 0.59. So that brings us over here, which means that this down here must be 0.41. All right, so again, here's an example of it, being a little more complicated, a little more going on. It's sort of branching in different directions to model what happens in real life. Now, question B says, what is the probability that the serving player wins the point? All right, so we've got to figure out what branches that involves and then calculate those probabilities. So we can win the point by getting our first serve in and then winning. So that would be this one right here. Or we could win the point by getting the first serve out, our second serve in, and then winning the point. All right, so there's 2 situations where we can win the point and 3 situations where we can lose the point. Now, to find our probability, we're just going to do our multiplication rule. So 0.59 times 0.73, that deals with this branch right here, plus 0.41 times 0.86. All right, but because our second serve was conservative, we have a lower chance of actually winning the point. So it's only 0.59. And then it's just a matter of plugging that into our calculator and seeing what it works out to be. So we've got 0.59 times 0.73 plus 0.41 times 0.86 times 0.59. And all together we get 0.638734. Or put another way, we'll say like 63.9%. The serving player is going to win the point. All right. So again, I hope this was helpful. If you have any questions, just let me know, and we will go from there. All right. Have a great day.